Hello, statistician. Today we're going to be talking about setting up a one sample z-test for a population proportion. This is Module 4, Lesson 4 in my notes, and you can find this in topic 6.4 through 6.7 in AP Classroom. Today we're going to examine the link between a two-tailed test and a confidence interval. So let's look at Part A. According to a National Center for Health Statistics, 36.6% of U.S. adults eat fast food on a given day. Part A public health director wants to know if this figure is different from adult residents for a particular county. A random sample of 150 adult residents from this county finds that 66 residents ate fast food on a previous day. What conclusion should the health director make based on the p-value at the 5% level? Assume the conditions for inference are met. Let's look at that first. So, like any test, we want to run a set of hypotheses. We're going to do a shortened version of this so we don't have to sit there and do the all four steps to calculate the p-value and make a conclusion. As with any test, we have to set up a hypothesis. So it's always a good practice to set up your HO and HA. And because we're talking about a percentage, that's your true proportion, that's your parameter. So we're going to say P equals 0.366. And because of the word different, that's going to be a two-tailed test. So we're two-tailed test. So we're going to say P is not equal to 0.366. So it's important to know what your hypotheses are in this case. As we set this up, we want to make sure that we can calculate a test statistic and a p-value so we can make an appropriate conclusion. Because it also says the conditions for inference are met, we don't have to actually check those here because we were told that they're already met. So let's set up our test statistic. We first have to have our sample proportion. So our sample proportion is, in this case, 66 out of 150. So we'll write p hat equals 66 over 150. Let's pull out our calculator and see what we can do. So these are all the numbers that we have to work with. The first thing we're going to do is let's go into our stat menu. And this is going to be under the tests. This is the TI-84 calculator. So if you have a different calculator, you want to make sure you know which, test you're going to be doing in there. And this is going to be a one proportion z-test. So we're going to do option 5. So my null hypothesis is going to be the PO, and we'll type in 0.366. The X and the N is the sample. So the X is the large counts, the 66 in this case, and the N will be the sample size, 150. Because this is a two-tailed test, I'm going to leave this as not equal to, and I'm going to go down to calculate. It's going to give me a z-test statistic, a p-value, and a sample proportion, which is the 66 divided by 150. So let's write that information down. In this example, I'm not going to go over the hand calculations for this. If you want to know that, you can look at my previous videos. In this case here, we have our p-value of about 6% and our test statistic about 1.881. So we want to see what kind of conclusion we're going to make at the 5% level. And if you remember what we looked at in our last video, we'll remember that that's going to be a relatively high p-value based on your significance level. So what conclusion are we going to make? Let's look at this template that I made. So since the p-value of, what is our p-value? Well, it's going to be, in this case, 0.06. And because that number is actually greater than alpha, in this case here, we're going to fail to reject the null hypothesis. We do not have enough evidence. And after the convincing evidence, we want to make sure that we talk about the alternative in context. So we do not have convincing evidence that the proportion is not 0.366. So we do not have convincing evidence that the proportion who ate fast food on the previous day is not equal to 0.366. So that's our conclusion. So now we can run the same type of uh, logic, but doing a confidence interval as well. So let's look at part B. Part B asks you to construct a 95% confidence interval to estimate the proportion of county residents who ate fast food on the previous day. So I'm going to use the calculator's one prop Z interval again to calculate this. So notice that the one prop Z test for our inputs, we were able to put our null proportion in and our sample. If you go into your stat menu and go to one prop Z int, it'll use that same sample. So 66 over 150. We want to make sure that we have our confidence level set. So this is a 95. So we want to make sure your C level says 0.95. And in this case here, we get a confidence interval. Let's go ahead and write that down and make a conclusion. So we would write down the interval that our calculator gave us and make an interpretation. We are 95% confident that the interval from 0.36056 to 0.51944 captures the true proportion who ate fast food on the previous day. Now comes the question. Would we be able to make the same conclusion from our two-tailed tests that or two-sided test that we did with our confidence interval, and explain how? And the answer in this case is going to be yes. Since 0.366, our null, is actually contained in the interval, we do not have convincing evidence that the true proportion is different from 0.366. So if the 0.366 were outside of the interval, then we would have that same conclusion from our two-sided hypothesis test at the 95% level. So if you remember our alpha level at 5%, that's the complement to the 95% confidence interval. So it's what's left over. And the last part of this question is asking what additional information does the interval give that the test does not? And we can both reach the same conclusions from the test and the interval. But the interval, what that does in this case is it gives you a range of plausible values that the true population proportion could actually be. So you can say the interval gives a range of plausible values for the true proportion. Now, let me be clear. If you're asked to test a claim, you want to run a significance test. However, sometimes you do have to think about some values that that proportion could be, and that's where the confidence interval is going to help with that. Now that you've seen the link between those two types of tests and intervals, we'll more formally define what we have to do for a one sample Z test for P. So you're going to be asked questions like, is there convincing evidence? And when you see that type of question, that lets you know that we're going to have to run a test. And because if we're dealing with proportions and if you're doing one sample, we're going to name this test the one sample Z test for P. Your calculator will call it a one prop Z test. So in all of our types of procedures, we're going to have to name what we're doing. We're going to have to state the hypothesis and the parameter, check your conditions, perform your calculations, and make a conclusion. So it's going to be the same type of setup as we would for an interval. What the difference is that we have to set up hypotheses if we're running a test. Let's look at this example. A potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, that might be an important word here, so more, greater than, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. The potato chip producer has just received a truckload of potatoes from the supplier. A supervisor selects a random sample of 500 potatoes back from the truck. An inspection reveals that 47 of the potatoes have blemishes. Is there convincing evidence at the alpha equals 10% level that more than 8% of the potatoes in the shipment have blemishes? So the first thing out of the way is we have to name what we're doing. And because we have the words, is there convincing evidence, we're going to run a test. So that type of language is going to say we have to run some sort of significance test. And the name of this test, because we're dealing with one proportion, is a one sample Z test for P. So we're going to name that procedure one sample Z test for P. Anytime you run a test, you have to state your hypotheses. So when you're writing your hypotheses, you always write HO and HA. Your HO is your null and your HA is your alternative. So for your HO, your HO, you have your true proportion. We always write P equals. And because we're trying to test to see if it's greater than 8%, we'll start with the null that the actual proportion is 8%. And that means the alternative is going to be P is greater than 8%. So P is greater than 0.08. And we must define P. So P is going to be the true proportion. And in this case here, potatoes with blemishes. So true proportion of potatoes with blemishes. So that's your setup. You state your procedure and your hypotheses and parameter. Next, you must check your conditions. Our conditions are the same as any other test or interval we've done. We have to do our random, our 10%, and our large counts. So we'll write that out. And let's find in the problem where all three of those are met. So in this case here, was there a random sample? A supervisor selects a random sample of 500 potatoes. So we'll say random sample of 500. As far as the 10% condition goes, a lot of times that's just assumed. So we can assume that 500 is less than 10% of the truckload. And remember with your large counts, we always assume that the null proportion is true. So we're going to use our 8%, not our sample proportion. So our large counts, NP and N1 minus P. So our N is our sample size. That's going to be 500. So we have 500 times 0.08. And you can do that calculation in your calculator. And then we have 500 times 1 minus 0.08, which is 0.92. And let's see, 8 times 5, that should be 40. And this should be 460. And double check that math for me. But both of these are going to be greater than or equal to 10. So we've met our large counts. And remember what that allows us to do is calculate a normal distribution. So we can use our sampling distribution for our normal curve for that. Let's run our calculations. We'll first do it by hand, and then we'll use our calculator's test menu. So since this is a test, we have to calculate a test statistic. So we start with the Z test statistic. And remember that formula is Z equals P hat, your sample proportion, minus your null proportion, divided by the standard error of the statistic using the null. So P, 1 minus P, divided by the sample size. So our P hat is going to be our sample. So we have 47 out of 500. So 47 over 500. And what was that going to give you here? Let's use our calculator. That gives me 0.094. Okay, I can put those into the formula now, and let's calculate that out very carefully. Let me model how we would do that in here. So I use my fraction menu, so I'll do alpha y equals, press enter. And on the numerator, I'll do 0.094 minus 0.08. Scroll down to the bottom and do second x squared, hit that square root, and do alpha y equals again. And I can put the 0.08, and you can do 0.92, or you can just do 1 minus 0.08. Either one is going to get you the same thing. Close that up, and on the numerator, denominator, put your sample size. So that'll be your test statistic, and you can do all of that at once if you want. So that's 1.15, we'll say 4. That seems like an important number, so we're going to make sure we circle that and write the word test statistic on there. The next thing and the last thing with that is we calculate our p-value. And remember, this is based on a normal distribution. So remember that is really just the z-score. Now recall that this is a positive z-score, so we're trying to test in the more extreme value, which means we want to go above that test statistic, that 1.154. So we're going to calculate the probability in a standard normal curve that z is greater than 1.154. And remember, that's going to be your p-value. Let's use our normal CDF for that. So we're going to do second vars 2, and our lower this case will be the 1.154. We want to go to infinity, so 99999. Leave it as 0 and 1. And 0.1242, that's going to be your p-value. 0.124 is fine. Those are the two things you must have in your calculations, your test statistic and your p-value. And because this is a one-sided test, we do not have to double that p-value. So 0.124 is your p-value. You can also get that test statistic and p-value using your calculator stat menu. So if you go into stat, tests, one prop z test, your null is going to be 0.08. Your X is 47. Remember, there were 47 potatoes that had blemishes, and your sample size was 500. Our alternative was greater than, and you can do calculate or draw. I'll show you both. So calculate is going to give you not only the test statistic and p-value, but it's going to also give you the sample proportion, which we had already calculated anyway, and your sample size. You should probably already have those anyway. So sometimes I see that it's valuable to do the drawing part. So go down there and do that. So you can see exactly what it's calculating. And that should mimic the picture that I drew. It's going to give you a little bit more accurate picture when you use your calculator. So if you want to sketch that picture out, that's not a bad practice. But are you required to calculate a sketch for your calculations? The answer is no. It's not going to hurt you, but you're not required. You're required to list the test statistic, the p-value, and all of the inputs and things that you use to calculate it. So whether you use the calculator or by hand, you want to show that work. So let's make a conclusion. Our conclusion is based off of our p-value and our alpha level. So let's think about this little template. Our p-value, what was our p-value again? Our p-value was 0.124. Now, our alpha level was given to us differently. It wasn't 5%, so I'm going to actually write 0.10, but that's still going to be greater than. So since that's greater than our alpha, what are we going to do? Well, we're going to fail to reject the null. Fail to reject the null. That means we do not have convincing evidence that the alternative is true in context. So we do not have convincing evidence that the proportion of potatoes with blemishes is greater than 0.08. That's your conclusion. You always are going to take your p-value and link it to alpha and make an either rejection or fail to rejection. Try this, check your understanding, pause the video, and read through the question. Remembering that the procedure, hypotheses and parameter, conditions, calculations, and conclusions should be listed when you're doing all these. All right, I'm going to read this in 3, 2, 1. A June 2020 report says that 78% of U.S. students in grade K through 12 have reliable internet access at home. Researchers believe the proportion is smaller in their large rural school district. To investigate, they chose a random sample of 120 K through 12 students in the school district, and they find that 85% have reliable, 85 have reliable internet access at home. Do these data provide convincing evidence that the proportion of students in the school district who have reliable internet access at home is less than the national figure? Less than the national figure. And since we're not giving a significance level, we can just use 5% to compare. The first part, we've named our procedure. It's a one sample z-test for p. We know that because we're given a population proportion. We set up our null and alternative, so our HOHA, and p is going to be equal to 0.78. That's going to be our null, which means we assume from the beginning that 78% actually have reliable internet access at home. And the alternative, because we're trying to prove that it's less than, is p is less than 0.78. Always define your parameter. So P is the true proportion of students in the school with reliable internet access. So we have our procedure, we have our hypotheses, and we have our parameter. And those are all important to list at the beginning. And some books call this the state part. We state what we're doing. Next, we check our conditions, the random 10% and large counts. And this is sometimes called the plan part. We were given a random sample of 120 students, which we can assume that's less than 10% of all the students in the district. Checking our large counts, remember using our null proportion, 78%, 120 times 0.78, and 120 times 1 minus 0.78 give us both numbers that are greater than or equal to 10. So you want to make sure you write those numbers out and list that they're both greater than or equal to 10. That'll take care of your conditions. Next, let's check our calculations. We have a sample proportion of 185 over 120, which gives us about 0.708. So we'll use that in our test statistic. Remember where things go in your test statistic. Your value is your sample proportion and your mean is your null proportion. And you put your null and your sample size in your standard error formula. Let's go ahead and calculate that. Looks like our z-score is going to be negative 0.602. Negative 0.602. Finally, we can calculate our p-value. So second vars, normal CDF. Because we're going in the less than direction, our lower bound is going to be negative 99999. Our upper will be our negative z-score, negative 0.602. Leave it at 0 and 1 since it's z. And your p-value is 0.27358. So we'll make sure we write our p-value. Those are the two things you must have in your calculations. Let's go to our stat menu and test all that out. So this is going to be stat test 5. Our null is going to be 0.78. The X value will be 85, and the sample size is going to be 120. This is going to be a less than, so change your alternative to less than PO. And I'm going to go to draw in this case. Looks like I'm off. I want to point out something, and I'm not going to edit this so you can see what's the issue. There are sometimes issues with doing things by hand. And as you can see here, if you look at my calculation over here, notice that I put a 12 and I did not type the 120. So that gave me a wrong test statistic. Since I forgot that 0 there, I should have got a z-score of negative 1.903. So I'll fix the numbers right now, and that'll change my p-value. So that gave me a z-score of negative 1.904, and I'm going to go to my normal CDF and fix that. And I should get a correct p-value of 0.028. I thought that other one was pretty high, but I didn't really second guess it when I wrote it down. So with that correct p-value here of 0.028, let me go back to the test and make sure that that runs it the same way. So everything should be the same for my input. I'm going to go to draw. And notice that it says our one prop z test, negative 1.895 and 0.029. I'm a little bit off here. I'm just not having the day. But we're close enough that I think I'm within the margin of error being a little bit wrong. So let me just make sure everything's, yes, I'm a little bit off because I rounded my sample proportion, but I'm going to make the same conclusion here at the end. So about 0.028 or 0.029 would be fine, and negative 1.9 would be an appropriate p-value here, or test statistic. All right, so let's make our final conclusion. So since our p-value is relatively small, less than 5%, we're going to reject the null. In this case, we have convincing evidence that the alternative is true. So we have convincing evidence that the true proportion of students with reliable internet at this district is less than 78%. Well, thank you for watching this video. I hope it was helpful in understanding the setup for these, and go forth and do your math.